So yesterday, we were talking about algebraic methods, and I said I needed to finish with two results. A theorem in mathematics is something I know to be true that is provable. We're not actually going to prove these. I'm just going to wave my hands a bit and draw you some pictures and hopefully convince you as to why these two sentences are true. The first one is called the comparison theorem. I believe yesterday I made a comment to the effect of I needed to know about f of x and g of x for all x, right? I put a little asterisk next to it. This is really what that asterisk means. I don't care about for every x. I care about a sufficiently small region around x equals a. So when I talk about f being less than or equal to g in a region near a, I'm thinking about, a minus some small value, and then a plus some small value. I need a symbol for a small value. I'm going to use a Greek letter. I'll use delta. That's a lowercase Greek delta. And it just means a small value. So I think of my graph, and I have this point where x is equal to a, and I need to know what's going on near a. Just some small neighborhood around a. So I've got two functions. I've got f of x and I've got g of x. And all I know is that in this section, the graph of f is always above, or at very worst, touching. Always below, or at very worst, touching the graph of g. So I have this graph up here, g of x. And I have this graph. Maybe it does something like this. F of x. But at a, in this picture, I've drawn them to be the same. So I have actually f of x equals g of x at that point. But it doesn't matter because I'm not looking there. I'm only looking around. And no matter where I look around a, g of x is lower. Sorry, g of x is higher. F of x is lower. And so that means that the limit as we approach along f, whether I'm coming from the left or coming from the right, is going to be smaller than what happens as I come in along g. They don't actually have to touch. I could have a picture like this. As long as both of these limits exist and are finite, they're actual numbers, then I know that as I get close, this inequality that we had between f and g is preserved by the limits. So I can compare things when I'm doing my limits. Does this make sense? Anybody confused? Got any questions? Talk to me. This is the time to do it. The real meat of this comes in the next result. So this time, instead of two functions, I've got three. I've got f and g and h. And f is on the bottom, g is in the middle, and h is on the top, at least near our point A. Let's also suppose that the limit as x approaches A of f of x is the same as the limit as x approaches A of h of x. Let's call this L. I don't know what it is. We'll call it L. What about G? What should I get for that value? I should get L, the output, right? Let's use our comparison theorem. I know that F is smaller than G. So the limit as I go to A for F will be smaller than the limit of G. But the limit for F is L. So whatever this limit of G is, it's got to be bigger than L. Now look at H. H is bigger than G. So whatever the limit is, as I get closer and closer to A from G, should be smaller than the limit for H. But the limit for H is L. I'm trapped between L and L. Was there any room in there? So I got squeezed in to the same value. As a matter of fact, on page 101, we see a fairly nice picture at the bottom of the page. F is on the bottom, G is in the middle, H is on the top. And you'll notice that they don't maintain this all the way through. F is smaller than G, but over here it's actually H that's in the middle. But near A, F is on the bottom, G is in the middle, and H is on the top, on both sides of A, at least in some small area around A. And these two come together, so this one's trapped in the middle. It must go to the same value. There's no room in there. It's squeezed down to a single number. Why would I need such a crazy idea? This is one of my favorite examples for the squeeze theorem. I'm looking at what happens as x goes to 0 to x squared sine 1 over x. We looked at sine 1 over x already. And sine 1 over x, as we went to 0, went back and forth and back and forth and back and forth and back and forth and looked like an earthquake was happening on my paper, and I couldn't figure out what was going on. So as we get closer and closer to 0 for that part, that doesn't exist. But what about that? That extra x squared does something. And what it does is it's multiplying this fraction by something getting really small. As x gets closer to 0, x squared is getting small, right? But I don't know how to take this limit because this part doesn't exist. It was giving us something crazy like that. So, what do I know about sine? What is the biggest possible thing you can get out of sine? Any sine graph. You plug in a number, the highest value you get out of sine of x. You should have gotten an announcement on our Canvas page and an email from Ms. Beninati talking about a unit circle trig review. This is why we need that crap. You should go fill out the survey to know what time she should hold that review by tomorrow. So please take the survey so that she knows when to do this review. And if you're going to go and brush up on your trig, this is a great time to do it. Yeah. The highest value a sine curve gets is 1. What about the smallest value? Because they bounce back and forth between 1 and -1. As a matter of fact, all of that bouncing is between -1 and 1. I'm just a crap artist. So I know that sine of stuff is trapped between -1 and 1. Always. Let's multiply by x squared. Now, I don't know how to take the limit of the thing in the middle, but I know how to take the limit of the thing on the left and the thing on the right. What do I get for those two limits? I get 0. Because these are polynomials I can just plug in. Hey, wait a minute. The bottom function gives me L. The top function gives me L. What has to happen to the thing in the middle? It's got to give me L as well. Even though I never actually calculated this limit directly, I could calculate it indirectly using the squeeze theorem. On page 102, we actually have a picture of these 3 equations. And you can see minus x squared is the parabola going down, positive x squared is the parabola going up, and there's the x squared sine 1 over x. Bouncing back and forth like a maniac. But it's stuck between those two, and those two match up at 0. In a lot of cases, dealing with limits is really about indirect measurement. I don't want to just go, okay, here, because I might not be able to. And this is exactly an answer of that. I cannot actually calculate this limit directly, x squared sine 1 over x, but I can calculate it indirectly. Questions? Okay, that was the thing I missed finishing yesterday. And that means that for the next hour, I will answer any questions you have regarding chapter 2, sections 1, 2, and 3 on any of the homework questions or just in general. So what questions do you have for me, Fiona? Oh yeah, absolutely. And if it's one of the ones that's assigned as homework, I'll do like the one before, the one after.
So I was trying to 4D.
For which section?
2.1.
4D in 2.1. So that says we're looking at a curve and now we want to draw a picture, right? So let's take a look in the exact same idea at number 3. So in number 3, we're given the point P 2 negative 1 on the curve y equals 1 over 1 minus x. And then we're asked to find a bunch of secant lines, right? So they give me x equals 1.5. And then later on, let's pick another one at random. How about number 6? They give me x equals 2.1. So I'm going to make secant slopes and all that fun from here. But in order to make my life easier, I'm going to start by graphing this. Just the equation itself. Here it is on the standard window. And that's absolutely no help to me, isn't it? I really only care about what's going on near x equals 2, right? And I know the y value is negative 1 because that's our point P. So I'm going to go and zoom in around close to 2 and close to 1. I just move my little cursor until it's close to 2 and 1. And then I hit enter again. Oh, wait a minute. I screwed up. I went to 2 positive 1. I wanted to go to 2 negative 1. So let me go back to the previous picture, zoom previous. Let it draw that again. Now let's do that right. Zoom in, move over to 2, and down to negative 1. There. That's the point I'm looking at. Yes? The point 2, negative 1. Right there. Now, I want to take those other x values and I want to build a secant slope, right? So I want a slope of the point P and the point Q where this is the x value for Q. This is what you were doing in part A, right? So I need 1.5 comma something. I don't know what the something is, but I can use this. If I hit trace and put in 1.5, I get negative 2. Then I have a slope. And the slope, change in y, negative 1 minus negative 2, over change in x, 2 minus 1.5. Negative 1 plus 2 is 1 over 0.5. That gives me a slope of 2. Now I need the equation for the line. Y minus point equals m x minus point. So far, so good. I'm going to rewrite that so that I can put it in my calculator. And that means I'm going to get y all alone, and I'm just going to do it like this. This would be a plus 1. If I move it over, it'll be a minus 1. So far, so good. Let's do it again over here. I grab my calculator, I put in 2.1, and that gives me this disgusting thing. Ew. Hang on a second. That looks like it's a repeating decimal, yes? Means it's probably a nice fraction. 1 over 1 minus 2.1 is 1 over negative 1.1. Oh, that's 10 over 11. I work better in fractions. If you hate fractions, that's fine. Use a decimal. The problem is you're going to need to use a lot of decimal places to get a more accurate answer. I think if we work in fractions, we'll get an exact answer. It'll be a little more helpful. So, slope. Negative 1 minus negative 10 over 11 over 2 minus 2.1. This will be 11 over 11. So when I do the top, that's negative 1 over 11. And then on the bottom, it's 0.1. Wait a minute, 0.1 is a tenth. Let's actually write it as a tenth. Then I flip the fractions. Hey, look at that. My slope is negative 10 over 11. Just take the bottom fraction out, rip it out, flip it over, and then multiply. So y minus negative 1 equals negative 10 over 11 times x minus 2. That's my line. Move that over to make my life easier. Now I have two secant lines. You with me so far? So my goal is to graph the original curve, which we already have, and then on this picture, graph, in your problem, 3 lines, 2 secants, and the tangent line you came up with in part C. I only have the secants, I haven't done the tangent line, but I can literally go right in here and type in this equation, 2 parentheses, x minus 2 minus another 1. And when I graph that, we see it goes through the curve in 2 places. One of the places it goes through is the point P, 2, negative 1. The other place is the point Q. If I graph this one as well, parentheses, minus 10 divided by 11, parentheses, x minus 2 minus 1. Ooh, hang on a second, I fucked up. Oh, I see where I fucked up. Talk to me. That should be a negative 1/10, not a positive 1/10. I made a sign error, minus 1 to me. If that's negative, negative over negative is positive. This should be a positive slope, not a negative slope. And I can tell because that line looks all sorts of wrong, doesn't it? It doesn't look like it's anything near the way my curve is going. So let's go fix that and get rid of that negative sign. There's the original graph. There's the first line. Here comes my second line. It goes through at point P and it goes through just past it at 2.1. Those are the right lines. And then I should be able to draw one more line because you came up with another equation in part C. So I have original curve, secant line, secant line. I need the tangent line that you came up with in part C. Now, the problem is I don't know what the slope of the tangent line is, but if I'd done all the bits in part A, I would have been able to work out what the slope of that tangent line is. I think it's 1, but I'm not sure in this case. You're welcome. More questions, people. Ask me more things. Yes, ma'am. So number 16 asked me to draw a picture, right? So let's take a look either at 15, 17, or 18. Here are 17 and 18. Would you rather do 17 or 18? Okay, so if I'm going to do 18, right? Yes. If I'm going to do 18, I'm going to write down all of the things that the problem gave me as conditions for my picture. So we are told in 2.2, number 18. We are told the limit as x approaches 3 from the left of f, sorry, negative 3 from the left of f of x is 3. We are told that the limit as we approach negative 3 from the right of our function is 2. We are told the limit as x approaches 3 from the left of our function is negative 1. The limit as we approach negative 3 from, sorry, positive 3 from the right is 2. We are then told f of negative 3 is 2, and f of 3 is 0. That's weird. But I have two x values I want to be concerned with. The two x values are x equals 3 and x equals negative 3. Okay, ready? I'm going to start at the bottom of the list. F of 3 is 0. So there's a dot right here. F of negative 3 is 2. So there's a dot up here. So far, so good? Okay. Now, these two are both about what is happening as x gets closer and closer to 3. That's this side. This one is coming from the right. This one is coming from the left. As we get closer and closer from, which side do you want to do? Okay, so as we get closer and closer from the right, I should be getting closer to y equals 2. Now, I don't actually get to y equals 2 because there's no dot up here. The dot's down here. So if there's no dot up here, there should be a circle there. And I should be going to that circle from this side. Now, it's up to you how you draw this piece. You could come in curving down, curving up, wiggling. You could do it however you want. But I need something that touches this circle from the right. Maybe like that. What about from the left? Well, from the left, I'm going to negative 1. So that means there should be a circle down here. Oh, crud, I drew the number over it. Let's change that. Oops, I'll put the 3 there. And now when I'm coming from this side, I should hit this circle. And I'm not going to draw a big piece. I'm just going to draw a small piece for the moment. Now let's do the same thing at the left point. As we approach negative 3, I have these results up here. When I approach from the left, I should be going to 3. This is at 2, so I need to be up here at 3. And I'm coming from the left, so ta-da! What about from the right? Well, from the right, I should actually be going to 2. But isn't 2 where the dot is? 2 is where the dot is. Yay, so I can do this. Now, it does say it wants me to draw a function, right? Create the graph of an example of a function f. Oh, okay. I just need to connect this piece over here on the left to this piece over here on the right. And there's my graph. Does it have to be this particular kind of curvy thing? No. It just has to touch the dots and the circles from the correct side at the correct heights. You're very welcome. Well, it's always, I had somebody, one person one year just drew horizontal line, diagonal line. Worked perfectly. How you connect them at this point doesn't matter. Maybe later when we get to chapter 4, how they bend and curve will be something we can determine, but not yet. More questions? Yes, Fiona.
26 for 2.1.
This one? Okay. 26 for 2.2 asks me to use a table of values. Limit as t approaches 0 or something, 5 to the t minus that one? Okay.
Yeah.
That's this sucker. So pick another one in this section. Which one do you want to look at? No, I will actually. So we're going to 24. So 24 says to take the limit as p approaches -1 of 1 plus p to the 9th over 1 plus p to the 15th. Now, my first reaction is, you've got to be kidding me. My second reaction is, what if I just plug in -1? What happens? Say again? Well, no, unfortunately, these don't become 0, but they do 0 out in one way, but not another. That's why I was trying to make sure I understood. If I raise -1 to the 9th power, I get -1. So I get a 0 on the top. I also get a 0 on the bottom. So this is an indeterminate. If I plug in, I get 0 over 0. If I had the ability to do a crap ton of algebra here, maybe I could do what we did in the next section and algebraically try and factor this and simplify it and see what happened. That's going to hurt. Because I gotta have to factor something with a 9th power and factor something with a 15th power. I think I'd rather hit myself with the head with a 2x4. So it suggests I simply use a table. If I'm just going to use a table, then what we're going to do is we're going to pick p-values that get closer and closer to -1. And we're going to take those values and plug them in to this. So the very first thing I am going to do, if I'm going to make a table, is I'm going to go here and I'm going to take my table setup and I'm going to go to table settings, which is above the window button. Second, table settings. And I'm going to make sure that that independent variable is set to ask. That means I can put in numbers and it will give me the result. Then I go back here to y equals and I put in our equation. Unfortunately, my calculator is going to be unhappy with me if I use a letter other than x. So I'm going to change this to x. I'm going to put in 1 plus x to the 9th divided by 1 plus x to the 15th. Now, please notice my calculator actually writes those superscripts up there. If yours doesn't and uses an up caret, that's this symbol right here, you might have to put the 2-digit number in parentheses. So you have to do x raised to the parentheses 15th. Sometimes the calculator is stupid. I'm not even going to graph this, but there's my expression. Now I'm going to go to my table. Those are numbers we used before, but those don't help me because those numbers are getting closer and closer to 0, and that's not what I want. I want numbers that are getting closer and closer to -1. If I use 0, I actually do get a number 1, but I want to get to -1, so how about we go -0.9, -0.99, -0.999, -0.9999. Please notice the round off error that happens in my calculator. This column of digits can't store more than 5 things, and the minus sign takes one of them. So I typed 5 nines and a minus sign, and it wrote -1 because the calculator is stupid. I'm going to write down all of the values that I've typed in. And then I'll type in the Y values we got. And I can do that by going here, and I can give you as many decimals as you want, because all of those decimals are stored across the bottom there. I don't know how many decimals we need, but I can write down at least 3 or 4. 0.7714, 0.61799. Oh, hey, wait a minute. 0.601799. Oh, hey, I see a pattern going on. Minus 0.600, I'm sorry, positive, not minus. 0.6001799. Down here, oh, it's even 0.6000017. What do you think they're closing in on, Fiona? What are they getting closer and closer to? Okay, I think we're going to go to 0.6. But all of the numbers I picked are ever so slightly bigger, so I should do some numbers that are smaller. I've only done an approach from the right. We should do an approach from the left as well. That's all you have to do in this case, is make this sort of a table. In our case, for this other function, 5 to the t minus 1 over t, right? Now, that may give me a number that isn't quite so obvious, but the more decimal places I write down, the more pattern I might be able to see. You're very welcome. Later in chapter 4, we will find a way to do this that does not require me to make a table, nor does it require me to do all this giant factor. There is an easier way to do this, but I got to build up a bunch of machinery between now and then. I need derivatives, and I'm not there yet.
Problem, so to confirm our results correctly, like, would you want us to draw a graph with that, or like, would we need to put our graph on?
It wouldn't be a bad idea to put the picture there, but this is all I got when I drew the picture. So if I zoom in on that, then I see what's going on near -1, can't I? There we go. I can even stretch this zoom further, because you'll notice nothing's down here. We think it's about 0.6, right? So I could even go so far as to take the horizontal line, 0.6. Let's see if the graph, oh, it does look like it crosses right at -1, doesn't it? I love being able to verify this. Is anybody here a chemist? Okay, good. There's a bad joke about enthalpy diagrams that look like elephants under blankets, and that's this picture. But since I'd already put it in as y equals, I had it in a convenient place to get the graph.
Okay.
You're welcome. More questions, ask me more things. Reason I bring this particular hacky sack to do the examples with is because it's a friendly one. Until we start getting things wrong. Same hacky sack, just a different perspective. Yes, ma'am. We're 16. So 16 is this one.
Also magnet subscript.
In this case, no. If there's no plus or minus, what does that mean? Both sides. That's exactly right. So here we're knowing what's going on both sides. Both sides. Oh no, that's one side. That's from the left. That's from the right. There we go. Absolutely. There are 2 copies of this textbook in the Math Enrichment Center in Reeves. So if you forgot yours on a day you want to look something up, walk on over to Reeves in the Enrichment Center. They're actually in binders, not hardback copies, because I got loose leaf copies from the book company, and I hate loose leaf copies. So I put them in the book center, so everybody, the math center, so everybody could use them. An interesting story. The person who wrote our textbook, James Stewart. James Stewart sold a lot of this textbook. As a matter of fact, this is the most popular calculus textbook in the world in terms of number of sales. Stewart made millions off of this textbook. Stewart is also a musician. Where have you seen this symbol related to music? This is the hole in the body of the side of a violin. It's designed to be tuned to a certain note, and in particular, this is tuned to F. Violins are tuned to F, so that's called an F hole. But it's also a mathematical symbol that we will use in chapter 5. Stewart's house, built by this calculus book, holds a musical auditorium tuned to F for the violin that he would play. The house is $30 million. If you want to be impressed as hell, Google the calculus house. You'll find it. The house that calculus built. It's a remarkably complicated looking building, beautiful acoustics, wonderful seating. This book paid for it. Unfortunately, Stewart passed away 2 years ago, which is why He's not the only author anymore. They gave some other people and said, we want a new edition. Stewart was working on it. He died in the middle of it. They gave it to two other people to finish. So Clegg and Watson actually worked on the book with him and then took over for him. I really liked the 8th edition. I didn't want to change. I have a half an hour left of time with your name on it, but I don't have a reason to nail your butts to these chairs. So I will be glad to stay here and answer questions, but rather than you just stare at me, if you don't have questions, feel free to keep working. I'm going to stop the recording and I'll start it back up if you guys have a question, but I should do something. Please note, tomorrow you are to hand in physical pieces of paper to me. There's no electronic submission for this assignment.